Okay. I guess you're not the people to ask why there's nobody here, because you're the people who are here. Not how I imagined it, but whatever. I guess we better get moving. Maybe there's some other class running late. Hi, I'm ready to start. Thanks. Okay, let's get going. Hi. All right. So that's good. I hope everything's going okay. Let's see. The midterm evaluations, are they open yet? I put some some questions on there about just trying to gauge the different parts of the class. So if you have any feedback you want to give me about how the class is going, that's a good way to do it, and I'll take a look at that and try and figure out what to do. I had some feedback that the grading scheme was possibly a little bit skewed. In particular, I guess at the moment it's like 20% for the presentation and 20% for class participation and 30% for the mini project, 30% for the final project. And I think that was I set that scheme at a time when I was imagining a smaller class, and when consequently each person's presentation would be a larger event. And so now, because the class is bigger than I anticipated, the presentations ended up being kind of less work. I mean, they're less work, but less time. They're less extensive. So possibly that's skewed. We could shift that around. I'm not sure of the legitimacy of changing the grading scheme sort of midway through. But I was thinking we could possibly shift 10% from the presentations onto the final projects, because I think the final projects is where I want you to, really focus your effort. But it doesn't make that much difference, because there's a fair amount of subjectivity in the whole grading scheme. I don't know if I should say that or not. But it's not like, it's going to be down to the last significant figure or something. When I do the final grading, I'm on the one hand, it's quantitative grading scheme where I put together numbers for each part of what you've done. I add them together in the specified proportions and get a final number. On the other hand, I then look at it and check that it makes sense. And it's not like, well, this doesn't seem right, but I'm going to ship it anyway. I don't release grades until I'm satisfied with them. And it seems like that would be an impossible situation, but it always works out. Okay. It seems like if I said I've got this numerical thing and it doesn't make sense, then what am I going to do? But somehow it always works. So I wouldn't worry too much about the details of the grading scheme. It all comes together in the end. Okay, any questions or comments before we get started? Okay, so this week's lecture is on filters and reverb. Sorry, I'm just going to get my clicker here. And these are, on the one hand, they're kind of the most direct application of signal processing to the use of signal processing in audio processing. I got it here. On the other hand, they're kind of some of the most powerful and ubiquitous things you can do with audio signals. So what we're talking about is taking the kinds of filters that we would study in signal processing in DSP and just applying them straight up to audio. But on the other hand, we're talking about a wide range of pretty important and kind of staple recording studio effects. Equalization, time delay effects, including things like chorusing, and then reverb, which is also kind of, it's in the same continuum, but it's a more complex thing, which is the simulation of room acoustics, and is extremely important in recording. So, the goal today is just to make a connection between these kinds of, these things that you can understand from an acoustic or from a perceptual point of view, and the actual underlying signal processing, which is a pretty direct link. So, there we go. Okay, so EQ, equalization, is, a big part of what recording engineers do. And so if you ever look at a mixing desk, like these 24-channel mixing desks, they'll always have a block of controls like this, which is the EQ section. And it's basically like, the treble and bass controls on your hi-fi or whatever. There are a few knobs here to control the level of energy in different frequency bands. Because it turns out that particularly when you're mixing signals together, the bottom of the mixing desk is a bunch of sliders to change the relative level. But it's not just the overall level. It matters what the relative level of signals are in different frequency bands. And so if you have signals coming from different sources, like a singer or a guitar or a piano or whatever, it may be that they need to be adjusted slightly in different frequency bands to get the correct balance, so that all the sounds remain, all the sources are equally clear and distinct in the way that you want. And so, typically you'll have something which is a parametric filter, a filter where you can control it by these parameters, but its frequency response is going to look something like this. So if this is frequency and this is gain, then you've got filters which you can either boost the frequency or cut the frequency. Then you'll have several filters at different frequencies, but you can actually also change the center frequency or the cutoff frequency for these ones, and maybe even change the bandwidth for these. So that's what's called you'll have, typically on a mixing desk, you'll have some fixed filters, but then you'll have one or two sections of parametric filter that you can vary like this. Another way that filters are, EQ is commonly encountered and used in a recording environment, is a so-called graphic EQ, which is just a set of bandpass filters with sliders to control the gain. And so what you end up with typically on a log spacing or an equal numbers of bands per octave. So this is like, I guess, it's normally typically the most useful one is a third octave, so three sliders per octave. And you set something like this, and it ends up being like you're drawing an actual frequency response, on a fairly coarse axis. But this is actually kind of turns out to be what the level of control that is very useful for a recording engineer. And you'll see less dense versions, which are also can be important and useful. And all this is just a set of individual bandpass filters and then mixing the results. And in principle, that's pretty straightforward. The only thing you have to worry about is what happens at the overlap between two adjacent bandpass filters, because then you're mixing two signals with overlapping frequencies, and you have to worry about the phase, because if the phase is if they're in phase, then they'll reinforce nicely. If they're out of phase, then you can get cancellation. You can get unexpected dips. So how do you actually build a filter like this? In particular, a filter that can both boost and cut frequencies, depending on how you set the slider. If we were building this now from scratch in PD or in MATLAB or something, we could do something very simple. Like in theory, we could take the FFT or a short time Fourier transform, and we could just adjust some of the levels of the frequency. We could apply a gain factor to different frequency bands and resynthesize, and we could do that differently for different frequency bands. But that's a relatively recent possibility. The origins of this kind of audio equalization are in analog electronics. And so there's some interesting, historically interesting circuits and approaches for building variable equalizers based on things you can implement in analog, which means basically poles and maybe some zeros. And this is the classic approach, which again relies on this idea of messing with the phase relationships between different signals to get different results. Yeah?
So nowadays it's mostly done digitally?
Well, it's I guess in most cases it's done digitally, but that still leaves the question of what the algorithm is. And I don't actually know, but the thing about when you take a system, when you take an analog system, so the analog systems typically use mostly poles, and as you remember from DSP, so a pole system is an IIR system versus an FFT-based system it's actually an FIR system. It's equivalent to that. And IIR systems are normally much more efficient, that they use maybe 10 or 100 times fewer operations per sample to get what you want. So, if you've got an equalizer on your MP3 player or something like that, that's not, I don't think that's taking FFTs and messing with it. It's almost certainly implementing some kind of IIR filter, which is an analog which is an equivalent to an analog filter. Because that's just like, we know how to do this. These circuits are pretty mature, and so the easiest thing is just to implement it. In that case, like in the iTunes equalizer or something, I don't actually know how they do it, but it's going to be a set of bandpass filters. But I don't know how they get the difference between boost and cut. That's the it's easy to build a bandpass filter which lets through a set of frequencies, and then it's like, well, I just apply a gain to that and it'll let through more or less of those frequencies. But what you really want is a system so that that it's very flat when you have nothing, and then you can either boost some frequencies or you can cut them. And that's that's a slightly tricky thing to do. So here's one way of doing that, which is kind of interesting, which is to have a system which has a flat gain response, but has a non-flat phase response. And in particular, for some frequencies, it might have a phase that's pi radians or 180 degrees or out of phase. And so if you take a filter but only at certain frequencies, you take a signal like this, if you add it to the original signal, when the phase so its gain is 1, right? It's got the same, at any given frequency, the amplitude of that frequency is the same, but the phase is not the same. Where the phase is 0, if you add it to the original signal, then it'll reinforce and you'll get twice as much amplitude. But over here, where the phase is pi, 180 degrees out of phase, when you add it, it cancels out. But if you subtract it, it goes the other way around. So if you subtract it, then this is the part that cancels out, and now this one reinforces. And so you can get a filter like this, where if you have this all-pass filter here, then you have a gain which can vary between plus and minus 1, adding or subtracting. Then by varying this gain, which is an easy thing to do, it's just a variable resistor, you can get a family of frequency responses which look like this. So if the gain is 0, then this path disappears and you just get a flat response. If the gain is 1 here, then we get cancellation at high frequencies because that's where it's out of phase, and reinforcement of boost in low frequencies. And in fact, because this is, at the low frequencies, this is essentially just doubling the amplitude here. Doubling the amplitude is raising the level in dB by 6 dB. And of course, cancelling it out is lowering the level by infinity dB. So that's plus 1. So plus 1 down to 0 sort of just fades this low pass response more and more flat. 0 is flat. And then as we go negative, we're cancelling out the low frequencies now and at the same time boosting the high frequencies. And so we get this set of high pass filters. And then the crossover point here, the frequencies at which they change, depends somewhat on how close these. So this is what the shape of this phase response is. The system that has this response, flat gain but variable phase, is an all-pass filter. And an all-pass filter is a filter that has poles and zeros in reciprocal pairs. So the poles, you have poles, but they're all inside the unit circle. They have to be inside the unit circle for a stable digital filter. So you have zeros at the reciprocal radius, is 1 over that radius. And then with this configuration, you get a gain response that is actually the sort of the effect on the gain of the pole and the zero just balance out perfectly on the inner circle, so that the gain stays flat. But their phase responses don't balance out, so you get this phase response. And so that is the basic idea. And of course, it's a very simple system to implement. So we can look at this in PD and listen to it. Let's have a go at that. Okay. So I'm using here this unit called fexp, which is this sort of very, very flexible thing that will do any kind of you can write any kind of expression in here. Fexp has the property that it, we spoke a little bit last week about how PD actually breaks up the samples into blocks and then processes each block one at a time. And that might mess up with a system like this where you actually want to take, recent values of the output and feed them back. But fexp is an implementation that actually works sample by sample. You put in an expression here, it parses it out, and then it actually applies that on a sample level to the signal. And what it's doing here is, the actual inputs depend on what you put in the expression, but it's saying there's one input x, and there's another input which is just a constant f2 because it's the second input. Then there's the output y, and so the output is now minus the constant times the current input plus the previous input plus the constant times the previous output, which is actually that's how you implement a first order all pass. It's got one pole and one zero, and they're implemented in complementary places. Yeah. F2 is just this. This is the constant, right? That's F says this is not a audio rate signal. This is just a fixed signal, fixed number, and the number refers to which input it is. If I put an expression here with extra numbers in, this thing would have magically generated extra inputs, right? fexp is kind of weird, but it does its job quite nicely here. And then it has the syntax to indicate which time point you're referring to, right? So I guess I did not put that in the slide. Yeah, well, it's not terribly informative. It's not terribly interesting, but that is, in fact, that's the correct way to implement this all-pass filter. If you look back at the definition of first-order all-pass filter, you'll see that's what it is. Let's just listen to this and see what it sounds like. So the easiest thing to do is to actually put in noise and see what it does. So, okay, so this is white noise coming in. And this is with the gain equal to 0. So this is just the flat white noise. And we see it looks kind of noisy, and the spectrum is flat here. But if I push up the gain like this, then you see it becomes this low pass response here that we're just getting low frequency. You can't hear it very well because of the transfer of the speakers. But you can hear it becomes this kind of more of a roaring sound. And the other way around, because the roll-off down here is kind of low, when I push it this way, it's just removing some of these low frequencies, but you don't hear that very much. But you can hear the balance. And if I change the pole radius, now it's not quite so dramatic a low-pass filter. And the complement is more hissy. You can hear better the difference between no effect and the high-pass, low-pass. If we do that with speech input, again, we can get something that sounds more like a parametric EQ, which was either being shifting between high pass and low pass. Okay, so that gives us one way of how to do this equalization, and shows us how to implement it in PD. So here's the actual the details of how this filter is built. Again, this is from the DSP class. The condition for an all-pass filter is that the magnitude of the frequency response is 1. Right? It's just the phase that's not 0. And it turns out that the way you build this is with the so-called mirror image polynomials, where you have one polynomial in Z as the denominator, and you have the same polynomial but with the coefficients flipped around for the numerator, which is actually, if this is some polynomial in Z, then dm of Z to the minus 1 is now, if this was in increasing powers of Z, this is in decreasing powers of Z. And if we shift everything back by Z to the minus m, then they end up being the same sort of range of values, right? If the highest... is that right? You have some term up here, so that if this is between Z to the minus 1 and Z to the minus... or 0 and Z to the 0 and Z to the minus m, then this will be between Z to the minus m and Z to the 0. So it's the same range of delays that you're talking over, but just the coefficients in a different order. So for a first-order system, the simplest all-pass system, which has a single pole and a single 0, we can choose a polynomial like this. dm of Z is 1 minus 0.6 Z to the minus 1, which means we have a filter, an overall system like this. Well, here's the 1 and the minus 0.6, and now it's the minus 0.6 and the 1, right? So the coefficients are in mirror order. And then this is the pole 0 diagram. So this goes to 0 when Z is equal to 0.6. So here's the pole. And then this is, the 0 is when 1 over Z equals 0.6. So here's the reciprocal 0 out here. So that's just saying what we said before, that the condition for an all-pass filter is to have reciprocal poles and zeros. It turns out that also is equivalent to saying that we have mirror image polynomials. That the polynomials have coefficients in reflected order. Here's the same pole 0 result for a different choice of alpha here. So this is alpha equal to negative 0.6 instead of plus 0.6, and so now the pole is over here and the 0 gets reflected out here. And here's the magnitude response is 1 for both of these, but the phase response, this is the one we had before, with the pole close to 0, where the phase changes rapidly and then sort of levels off. And for the new one, where the pole's on the other side, the phase changes slowly and then suddenly changes more rapidly as we get close to the high frequency. Obviously, the absolute value of the phase is important in terms of achieving these phase cancellations. But there's also an important effect of the slope of the phase. It turns out that if you, so a fixed, a delay, right, so a pure delay signal is what we call a linear phase signal or a linear phase system in DSP. Because it just has a phase function which is straight. But a phase function that curves like this, what that's saying is that the different frequencies are being delayed by different amounts, because it's the actual phase here is the delay, and so these are not on a straight line, so they're not having a constant delay with frequency. And so you have this effect of what happens when you delay the adjacent frequencies by different amounts. You affect the envelope of those frequencies, and it's called group delay. And the actual, the definition of group delay depends on the slope of the phase function, not the absolute value, but the slope. And there's this difference between group delay and phase delay. If you put in a sinusoid and look at its fine structure, look at how much the actual 0 crossings get delayed, and that's just the phase response here, the actual value of this curve. But if you modulate that sinusoid, you put some kind of envelope onto it, put it through a system like this and see how much the envelope gets shifted. That actually goes by the group delay, the local slope of the phase function, not the phase delay. So here's a picture illustrating that. If this sinusoid here was going through a pure delay signal, its phase response would look like this, and it would be delayed by however many radians this is, which is whatever this particular delay corresponds to in terms of the period of this sinusoid. But if the actual system has a response like this, where you have a local slope which is different which isn't just connecting it to zero, then the effective delay of the envelope of the signal in this region it depends on that slope, and it's the group delay. So in 4810 in DSP, we had an example of this. Let me just play that example quickly because it's kind of interesting, and it's a simple thing to do. So this is from the DSP website. And then here, what we do is we just build a single complex pole, and then make it into a conjugate pair, and then we have the mirror image version of that by just doing flip, by reversing the order of the coefficients, and then we make a filter that has that denominator and that numerator. Let's just run this in MATLAB. So that's the hang on. Okay. So this is the magnitude response, and this is the response to the filter. The magnitude is 0 dB. It's a flat filter apart from these numerical errors. But then we have this phase response, which is non-flat. If we look at it in the z-plane, then we have these two poles and these two reciprocal zeros to give it this is now a second order all-pass system. And then MATLAB has this function, group delay, to actually calculate the group delay. All it's doing is taking this phase function and effectively differentiating with respect to frequency. But this nicely illustrates the response that here was the peak negative slope in the phase function, which means that if the group delay is the negative of the derivative of the phase function, that's where it has its maximum. And the group delay is actually, the units are in samples, so it's saying for this frequency at 0.1 of the Nyquist rate, we have a delay of 20 samples, and then the delay is close to 0 for most other frequencies. Now, 20 samples is not a huge deal, but if we repeat it, if we repeatedly apply a group delay function, well, the magnitude response is flat. So the energy at every frequency stays the same, but the group delay accumulates. Right, so if we start off with this
cottage cheese,
well-known sound example,
delicious.
We can copy that into some temporary variable here, and then what we can do is we can apply this filter 100 times over to that signal. And then we get this.
Cottage cheese with chives is delicious.
And we can, in fact, keep doing it, right?
Cottage cheese with chives is delicious.
So there's something very weird going on there. And then if we look at the actual spectrogram here, you can see what's happened. So here's the spectrogram of the original signal. It's a speech signal, and we see these onsets at the beginnings of every syllable, every different speech sound. And then here's what happened after we put it through that filter 200 times, which meant that if it was delaying it by about 20 samples for each time, then 200 is 4,000 samples, and this is is that right? Yeah, that's right. This is a 16 kilohertz signal, so 4,000 samples will be a quarter of a second. And you can see that now in the region of this frequency, this peak in the group delay, which was 0.1 of the Nyquist rate, so at 800 hertz, we got a delay of about a quarter of a second. But it's just local to all the frequencies in this band. And this band here have been delayed a quarter of a second relative to the rest. And so you still have, everything's still there. It's just that it's been sort of moved around in time in a non-uniform way. And what we hear is we hear the sort of these squeaking sounds as these energy peaks move up in frequency. Yeah?
It seems that we have more energy after we pass through.
It does, but that's just the color axis in that lab, right? So if I subplot 2 on 1, look at the color axis here, and then maybe set it to something like minus 60 to 20, and then subplot 2 on 2 and give it the same color axis, then they look the same, right? Just MATLAB does this auto scaling of the color axis because we pulled in this hole here. It was pulling energy when there wasn't, from before when it's 0. It has a much lower minimum, and so when it auto scales, it just pushes the scale up. Because, of course, the all-pass filter does not change the total amount of energy. It just moves it around in time. Okay, well, group delay is actually not a tremendously important studio effect. It seems like it could be cool, but it's not. People haven't figured out how to use it effectively. So you don't come across that very often, although maybe we should explore it. But here's our second order. So that was using a second order all pass. So it had 2 poles and 2 zeros. And now what that means is that you can have this kink in the magnitude response, and you can move it around in the phase response. You can move it around in frequency by moving the position of this pole 0 pair. And you can also change how sharp it is, how rapidly it changes, by changing the radius of this pole 0 pair. The further they are, the shallower it becomes. The closer they are, the sharper it becomes. Because there are actually two poles and 2 zeros, the terminal phase difference here is 2 pi. It doesn't really matter too much, but what happens is if you think about the phase at this point and you go all the way around the circle, and then you get the phase at the end, which is basically going all the way out to 2 pi over here. And what will have happened is, you'll have encircled these 2 poles, an entire circle, but you'll still be outside of the zeros. So the zeros will contribute phase that will change, but at the end of the day, you'll be at the same. It'll all have cancelled out. They'll sort of go up and it'll go down. But the poles, you started off here and you sort of wound your way all the way around. So the poles have accumulated a total phase of 2 pi per pole, which means that for omega equal to 2 pi over here, the total phase change is 4 pi. So for omega, and it's symmetric. So the total phase change at omega equals pi is 2 pi. Okay. Whereas on the previous one, where we only had one pole in the middle, the terminal phase was pi, was like 180 degrees. Now it's 360 degrees. So what happens is this is the point where you've got 180 degrees phase shift. And so if we add these two signals together, this is the point where we're going to get cancellation. And if we subtract them, it's the place where we're going to get reinforcement. So now we have a filter, it's the same structure, it's the same parametric filter, where it's taking this all-pass filter and then having a continuum between subtracting and adding it. But now the set of frequency responses we get is like this. When we add it, we get a notch filter. And when we subtract it, we get a bandpass filter like this, because we're cancelling out the two extremes. And we have, before we had one parameter, apart from the gain, we had one parameter, which was the radius of the pole. Now we've got 2 parameters we can change, the radius and the position of the pole 0. So let's have a listen to that in PD. So again, let's listen to just a noise signal going in there. Let's see if we can bring up the oscilloscope spectrum. Okay. That didn't sound good. Really? So I think that noise normally means that I somehow I'm not exactly sure what happens, but once that happens, PD, I have to restart PD. Somehow I hit a nan or something in the PD output, and it never recovers. There we go. Okay. When I restart PD, I have to redo the audio to send to the thing that'll feed it to the outputs. Okay, let's try that again. Okay, there we go. So now that, when I have the gain at 0 here, then the audio is just coming straight through and going straight out. But here's my second order all pass section with my pole, radius, and angle. So if I have a lower angle here, that's a lower frequency thing. So now if I have a positive gain, that's actually a notch filter. If I have a negative gain, that's a bandpass filter. Let's see if we can see that. So you can hear that going, becoming a high frequency bandpass signal. Because the sampling rate is so high, I have to make the pole angle very small to get, interesting frequencies. There we go. There we go. That's it. I blew it again. All right. You get the idea that I can change the I can parametrically vary that bandpass filter both in frequency and bandwidth, and then also in whether it's a bandpass or a notch. I'm not sure why it's blowing up there, right? That's normally what happens when you have an unstable pole outside the unit circle. That pole was not able to go outside the unit circle, I don't think. But something about it is misbehaving. Okay. That's for just stationary EQ. The idea of that is that you've got the mixing desk, you've got some sources coming in. You want to adjust where their energy, just have a fixed adjustment of the energy in different frequency bands, because there might be some particular source that has a particular peak and is either dominating the mix or it's not clear enough in the mix. And you can just move this with a parametric filter. You can just pinpoint on that one part and adjust it to make it sound better. It's actually a very kind of it's quite a rare skill to be able to what a good recording engineer, a good mixing engineer does. They can listen to the sound, they can figure out what it is that's not making it sound right. So they know they can translate their own subjective impression of what the sound sounds like into adjusting the frequencies and the gains of a filter to make it sound right. But there are people who achieve that. Another way of using filters is actually have a time varying filter. And one of the classic forms of this is the wah-wah. And this is a figure from the Daffix book showing the time varying frequency response of a particular wah-wah filter. So it's just a bunch of resonances at different frequencies, and then they're moving, they're modulated in time. So this is like modulated at 2 or 3 hertz, but they're just moving up and down steadily. And that this, by having these filters, which is sort of a bit like the resonances of the vocal track, you can end up with an effect that sounds a bit like, the effect of going wah, 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 because that's just moving your vocal resonances up and down like that. And that can be, because I know you could argue that because we're so attuned to those formants in speech, that it has a particularly powerful effect. So here, and to simulate this, all I've done is I've taken the VCF object, the variable filter in PD, and I'm just driving it with a variable frequency. So again, if we take the noise, yeah, here we go. So if I just have the straight the bandpass filter fixed, you can get different frequencies out like this. But if I add some low frequency oscillation in here, you can sort of begin to get some kind of the right frequency. It does begin to sound a little bit like you can imagine someone, there's someone speaking. But if you apply it to speech, then you can get a more powerful effect. I don't know how well you can hear that. But if we do it and then we try it on some music, right, so that's the Juno patch, right, just the strings patch. But then when we apply this time-varying filter, that's actually sounds quite interesting. So you get the idea of when you apply time variation to a filter like this, it actually, it brings a whole different kind of effect in, and you can, these can be quite useful and rich effects. Okay, any questions about that? All right, so that's just the classic the filter, the way that we were thinking about it in DSP as just a system that takes a range of frequencies and changes their relative energy compared to other frequencies, which is important and useful. But there's another kind of filter, another kind of system, which is more usefully thought about as a pure delay. It's still, you can understand a delay in terms of frequencies as well, but over some perceptual range, it becomes more relevant to us as a time delay rather than as particular frequencies. And delays are very physically relevant because of the finite speed of propagation of sound. So if you do have sounds which take multiple paths, like reflections in a room or something like that, the effect is effectively like putting it through a delay system. The speed of sound is about 340 meters per second, which is about 1 millisecond per foot. And so, if you have a single wall over here and you hear a direct path, a sound coming from my mouth to your ears, and then there's also a reflection from a wall, then it might have a path that's longer by 10 or 20 foot, something like that, and that would be a delay. It would be both a delay of 10 to 20 milliseconds and an attenuation due to the fact that not all the energy is reflected by the wall. But this is the kind of signal that we actually encounter in real environments. And so it sounds very realistic to us. From a signal processing perspective, a delay like this has an impulse response, which is just a delta of n minus tau, which means we can take its Fourier transform, and that's just we use the Fourier identity that a delay corresponds to a linear phase shift e to the minus j omega t. So as a function of omega, the phase is just omega times tau, the delay. And so here's the magnitude and phase response of that filter. It has a pure unit magnitude response and this linear phase response. So it's sort of like an all-pass, but it's not an all-pass because this is a system with only zeros and it doesn't have the nice wiggly phase, just has the sort of degenerate linear phase. If we want to delay a signal by one sample or 100 samples, that's pretty easy. We just do that with like a memory or a shift register. We just write in a sample at one point, and then however much later we read it out, as long as we've been keeping track of all the samples in between, then we can get a pure delay like that. Most audio, PD and CD audio is running at 44.1 kilohertz, and so one sample is 1 over 44,100, which is 22.7 times 10 to the minus 6, 22.7 microseconds. That's a pretty small time quanta, but it's not so small that we could never imagine wanting to have finer resolution than that. So sometimes you want to be able to build filters where you don't vary by whole sample steps, but you have some other duration. And although it sort of seems like suddenly that gets a lot more complicated, it's actually not that. It's not notionally that much more complicated. You could imagine having the system which was operating at a very, very high sampling rate, and you're just, delaying it by some integer number of samples at this super high sampling rate. But then you're sort of doing a resampling operation to reconstruct a signal at the actual sampling rate you're using. What that happens, the resampling operation would involve a low-pass filter, an anti-aliasing filter, and then decimation, throwing away the extra samples. The low-pass filter is, of course, just the sync impulse response, right? That we saw that when we were looking at upsampling and downsampling in DSP. And so you can do away with the intermediate sampling rate and just say, oh, okay, a fractional delay is just samples drawn from this continuous sync function, but now the sync function is centered on whatever actual delay I want. If it happens to be centered exactly on a sample, then the actual point you sample from here is 1, and all the other points occur at the zero crossing. So then you have an impulse response which is just the integer delay of samples, which is what we expected. But for any other value of delay where the delay doesn't quite line up with the sample, you actually get an impulse response where actually none of the values are 0, and but they die off with time as 1 over n, which is the decay of a sync function. So it's actually, on the one hand, it's not that hard to build a fractional delay. You just have to build this FIR filter, which is drawing points from a sync function. On the other hand, it's kind of a pain because to get a really good approximation, you have to use a pretty long FIR filter because these values die away quite slowly. So it's a lot more expensive than an integer delay, but it's not that bad. And then you at some point you say, okay, I'll take the error, you chop it off, you truncate it, and then you get a pretty reasonable fractional delay. Okay, so now we've got a block we can implement, which is just a straight delay here, and it can be either a fixed number of samples or a fractional number. So the things we can build with that, well, again, this is something we saw in DSP. If we have a system which involves delays which are not single sample but multiple samples, then what we end up with is a system which has a repeating frequency response, right? Because basically you could say, well, if this system was running at a lower sampling rate, which is just one sample per delay step, then it would have a frequency response that looks like this. But we're looking at it at a higher sampling rate, and so we see the sort of the periodic repetitions of the frequency response, which are intrinsic to the discrete time axis. So here's one such system, which is a pure delay, has an impulse response, which is just one, the direct path, and then this single echo. So it's like a single reflection off a wall. This is a comb filter, and this is its magnitude response. So what happens is, for frequencies where this period is exactly one cycle, then we're going to get a constructive constructive reinforcement between the direct path and the echo. And for frequencies where this delay is half a cycle, so that when we delay the signal by tau, it's now 180 degrees out of phase, then we're going to get cancellation. So you get this alternation between peaks and dips. And that's why it's called a comb filter, because the frequency response looks like a comb. And so the peak gain is 1 plus G, and the minimum, which is when they're reinforced, and the smallest gain is 1 minus G when they're cancelling out. And so if G is smaller than 1, then you get shallower dips here. And in fact, it's an FIR filter, which means it has zeros, and just what happens is these zeros become uniformly spaced around the unit circle, and each one of these dips corresponds to one of these zeros, and then as G goes to 1, the zeros get closer to the unit circle, and at G equal 1, they sit on the unit circle, and you get actual zeros. So this filter is not very complicated, and obviously you can vary tau to get different filters, but they're all conceptually equivalent. But perceptually, they have quite a range of effects. For very long times, for longer times, like more than 100 milliseconds, you can actually hear the second instance. And so that's like a slow echo off a very distant wall. You can hear there are two copies of the sound. For intermediate times, between more than about 20 milliseconds, but less than 100 milliseconds, the sound is different, but the echo is coming so fast that you can't easily hear it as a separate source. And so this is more of these effects of like chorus or doubling, where it sounds like maybe you've got multiple voices there, but you don't exactly know what's going on. And then for very short delays of less than 10 milliseconds, these notches become, this first peak is the frequency that has one period in the delay. So this first notch is the frequency that has half a cycle in delay. So if we have a 10 millisecond delay, this is going to be 100 hertz, and this will be 50 hertz. And if we have 1 millisecond delay, this will be 1,000 hertz. This will be 500 hertz. Then the effect of the comb filter switches from being kind of a time domain effect to being more of a spectral domain, and we hear different peaks and valleys in the spectrum. So it's quite interesting. They all come from a single continuum of systems. So let's just listen to that in PD and see what that's like. Okay. So let's do this with speech for now, just to, if you can bear to listen to that thing a few more times. Okay.
Cottage cheese with chives is delicious. Cottage cheese with chives is delicious.
So this is straight through.
Cottage cheese
Now,
with chives
here's my delay.
Cottage
I have a long
cheese
delay like
with
this.
chives is delicious. Cottage cheese with chives is delicious. Cottage cheese with chives is delicious.
You can hear that clearly as an echo. If I turn it down,
Cottage cheese with chives is delicious.
it sounds kind of plausible. Sorry. It does actually drive you crazy after a while, listening to that. But you get the echo effect, right? Let's just let our brains recover for a moment. I should use a longer sample or something, just so that the loop doesn't lock you in. But so I'm going to bring the delay down, and we'll hear it changing from being a clear echo to being something that sounds more like a chorus or doubling effect.
Cottage cheese with chives is delicious. Cottage cheese with chives is delicious. Cottage cheese with chives is delicious. Cottage cheese with chives is delicious.
So that, I don't know what that sounds like to you. It sounds to me like there's a little bit of depth or something to his voice, a little bit of texture. Let me just play that to you, and I'll vary the gain so you can hear, what it's like without the voice, and then with the voice, without the echo, and with the echo.
Cottage cheese with chives is delicious.
So that's dry.
Cottage cheese with chives is delicious. Cottage cheese with chives.
And that's with the echo.
Cottage cheese with chives is delicious.
Okay, so now, but then as we bring the delay down further still, we're going to get into this sort of phasing regime here.
Cottage cheese with chives is delicious. Cottage cheese with chives is delicious. Cottage cheese with chives is delicious. Cottage cheese with chives.
Okay. I don't know if you could hear that. It's kind of interesting, a nice studio effect, but we'll hear that better in a couple of slides. So let's just get through this. So that's a single feed-forward delay. So it's an FIR filter, just a single pulse in the impulse response. Another thing we can do is to have a feedback delay, where it's the same thing, still just got a single delay with a variable gain that we can put. But now what happens is, because it's feeding back, the impulse response is now an infinite impulse response, an infinite train of these echoes decaying exponentially. And rather than zeros, we have poles here. But they're still uniformly spaced on a unit circle. These are basically what happens if you take the nth root of z minus z. What is it? It's the roots of z to the n minus 1 equals 0. And so, but now these poles, now rather than giving dips in the frequency response, they give peaks in the frequency response. So you end up with another comb filter, but now it has a response like this, where now this is 1 over 1 plus g. So where it was going down close to 0, now it goes close to infinity, and then you have the dips in between. And so that has a different kind of effect, a different kind of sound. Okay. So again, now to do this, actually, sorry, I didn't show you that. To do this simple feed-forward delay in PD in the previous one, we have this delay operator, which basically just does exactly what we expect. You put samples in, has an internal buffer, it writes samples in, reads out the oldest one, and you start off with a parameter which is how many samples you want it to how large a buffer to have. But then you can feed in this thing a control time to say how many samples to actually delay by. With feedback, it's not so easy, because you have this problem of the sort of the frame level calculation. So we couldn't just take the output of that thing and feed it back to itself, because you'd end up with a loop that wasn't necessarily didn't necessarily have a delay in it. So PD has special operators to do this sort of feedback loop, where you have del write and del read, and they both refer to a single buffer, and del write writes samples into the buffer, and then del read reads them out. So their combination is the same as the delay operator, but now we can do it with this feedback structure. So here is the effect. Let's see what it sounds like. Why is that not working? Got the sound file loaded. Okay, so here's a long delay. Okay, and with a lot of feedback here, we get this. You can hear the individual decaying repeats, right? With a small small delay, it doesn't sound too artificial, but it sort of sounds more like room reverberation. It sounds very active. And then with a shorter delay like this,
cottage cheese with chives is delicious.
With a short delay, you get a lot of echoes, but they have a fairly long, they take a while to die out.
Cottage cheese with chives is delicious.
With a reasonable time like this,
cottage cheese with chives is delicious.
It can sound something like a sort of a small room, but as the gains get higher and the delays get shorter, then suddenly it turns more into this kind of comb filter, this filter of resonances.
Cottage cheese with chives is delicious.
And now you're getting the individual filter peaks coming up to be like just a set of harmonics. So we actually hear the pitch corresponding to the actual spacing of the peaks in the spectrum. So actually, if we look at this, if I feed a noise input here instead of the voice, let's turn it down a bit. All right, so as I go to a long delay here, then you just hear it as noise. You can't really hear anything going on. But as the delay gets shorter, you can now see the individual peaks of this bandpass filter, and you can hear the pitch. As I reduce the gain, I'm getting the peaks are going down, but as the gain goes up, they become more and more distinct. Okay. Let's see. Running out of time here. I guess these demos take a little longer than I expected. Okay, so here's this thing. If we actually have the delay and we vary it with time, again, this is the same thing, that we can take an effect, but when we add time variation, it becomes something different. This is actually one way of what we end up with is actually varying the pitch. And what it's analogous to is Doppler shift, because if the delay corresponds from sound coming over a different path, Doppler is when you have a sound source on a moving with you relative to you in space, and so the actual delay due to the propagation through space is varying with time. And what happens is the actual pitch the pitch can get changed as the sort of as the fire truck is coming towards you. It's emitting 100 or whatever, emitting 1,000 cycles per second, but it's it's got the added effect of it coming towards you. So each one of those pulses is taking a little less time to reach you. So rather than having them reach you every millisecond, they're every 0.95 milliseconds. And as it's going away, it's still emitting one pulse every millisecond, but now each one has a longer delay, and so they take slightly longer, 1.01 milliseconds, and the pitch goes down. So if you have a time-varying delay where you periodically increase and decrease, then you're sort of like getting this Doppler shift where it's pushing the pitch up and pushing the pitch down, and you can get this slight pitch shift. And then when you add that back into the original signal, because you've got slight changes in pitch, so you've got these, you can think of your signal as having these harmonics, the harmonics sort of shifting relative to one another, and occasionally they're cancelling out, and you get this sort of effect, which is very much like the sound of what happens if you have lots of people trying to sing the same note at the same time. They're almost on pitch, but there's a sort of little cluster of harmonics around every point, which gives you the so-called chorus effect. So we can do that, and this is a very important studio effect as well, and is a little bit tricky to implement, because you want to have these delays be short. You want to have them change by small amounts, and you don't want to have audible clicks as the amounts change. So to be able to implement this, you have there are a few things you have to do to make sure you don't get glitches. And so PD has a special object for this, variable delay object. So we have something that's writing into our delay buffer, but then we have this variable delay thing coming out, and then we have an oscillator here, which is actually just setting the delay, and has a few things in here. So let me use the synthesizer pad for this. So that's the straight pad, but then when I add in some of this now you can hear the pitch shifted version. if we just listen to the pitch shifter, the output of the delay, variable delay. So that's without any delay variation. So just a little bit, and then this is the cycle that I'm varying it at. Okay, so that is a more subtle pitch variation. And then when I add that back into the original, hang on. So you see it makes it sound much richer and it's a pretty powerful effect. And of course it can shift the pitch of any sound input because it's just doing it by, I mean, there's a small delay associated, but apart from that it's just actually, you know, stretching and compressing the waveform to get the pitch variation. Okay, so the last thing I wanted to introduce was reverberation. And reverberation is, again, you know, it is actually what we experience in rooms, and so, you know, you can characterize it as an impulse response. You can model it as being, you know, a combination of direct and reflected paths, which you can then describe as impulse responses, and you can generate this by simply building the impulse response or sampling it and then convolving it with the source signal, because this is exactly all that's happening when you have a single source and then some receivers out here going through a channel which has got reflections. It's just convolution. Whatever impulse comes out of here gets put through these reflections. So it's very simple to construct. You can have these models for rooms where you sort of imagine what's happening for every reflection. It turns out that if these were mirrors, right, which they're effectively a smooth wall is acting for sound like a mirror for light, then it's as if you've got these virtual sources, these image sources. If you're looking into the wall and you could sort of see it, then you sort of see a reflection of the source over there. And so one very nice way of quickly coming up with simulated impulse responses for rectangular rooms is this image model where you sort of draw this, you repeat the room, you reflect it on this grid, and then you have images of all the sources, and you just imagine that instead of having one source, you had a large number of coordinated sources all emitting sound at the same time, but they all have different paths. And so you just do the sort of the ray tracing, you figure out the distance here, that gives you the different delays. And you look at each time they go through a wall, you have some kind of low-pass filter and attenuation. But then you can end up with a theoretically very pure version of what the sound would be like when it reached the listener. Reverberant impulse responses, they're basically, you get multiple reflections, right? So it's more like the feedback IIR system, which is why that feedback comb filter with long delays sounded kind of like a room. And so they tend to have this kind of exponential decay in energy. Out here, it's very sort of just basically like a noise signal that's been decayed. The earlier part of the signal has a few discrete reflections, which are actually individual. You know, if you do it in a real room, you can say this is the reflection coming off a particular wall. And people are sensitive to this. If you vary these, the sound of the room changes. But they're not very sensitive to detail out here, because out here you can't distinguish the different reflections. There are a couple of ways of doing this. There's this nice structure which is a nested all-pass. It's a combination of a feedback and a feed-forward comb filter, but they're combined in such a way that the overall frequency response is flat, but the phase response is not flat. So it's basically just another kind of all-pass filter, but just done with a single delay and a couple of gains that gives you a structure that is all-pass but has a very complex phase function. And then you can actually take this whole structure and put it inside here, so then you can nest the all-passes and you get even more complex. And the goal in reverberation is to, with the minimum number of commutations, come up with the most kind of complex and noisy impulse response. And so this is a very quick way to build these up. But another way of doing that is to, rather than having a single delay line, you can actually have a kind of a mixture of delay lines. You can have several delay lines which are operating in parallel. Then you can feed back, rather than just feeding back to one of them, you can have this mixing matrix which takes the output of one and feeds it back to all three and mixes them together. And then you have this sort of all these possible, combinations of the output from one feeding back to the input of the other, and you get this kind of build-up of different echoes. And this has been empirically studied to find the ones that, to come up with combinations of these parameters which sound good. And that's what we'll be playing with on Wednesday. PD has several reverbs built in, but we'll actually take one apart and see what's inside and see how it works out. So that is pretty much it. We looked at use of filters, just as sort of doing what they're supposed to do, varying the energy and frequency bands, the different ways that different effects that delays can have in audio, and how the different classifications of those, and then reverberation as this way of simulating the sound of a room, which is very adds a lot of depth and quality to music recordings. Any questions? All right, so we'll see you on Wednesday to listen to some reverb and try some of the stuff out.